we will come back to the marked Poisson point process. So what is a marked Poisson point process? You can guess a Poisson point process where the points are marked uh, is known as the marked Poisson point process. And an independently marked Poisson point process is a point process underlying point process as a PPP. You can also have dependent marking also. Independent marking of a point, but let's focus on the independent marking. Independent marking of a point x with mark m uh, can be seen as an independent displacement of x to a new point x comma m in the space R cross. Okay, so if you see that you have a point and you assign a mark, so you are expanding the coordinate x comma m, and that's a point in the R cross m dimension. So it just means that you are taking this point and putting equivalent point in this space. So this is like a displacement. So we have proved that independent displacement of x result in a PPP itself. So the mark point process is nothing but a independent displacement of points. So it is also a Poisson point process. Okay, with a modified intensity measure with Campbell message measure. So independently marked Poisson point process is also a Poisson point process with modified intensity measure or Campbell message measure. Okay. To show this, we will compute the Laplace function of the marked Poisson point process. So the Laplace function of marked point process can be similarly computed. Remember that for a normal point process, Laplace function is given as expected value of exponential of minus summation of fxi. Here, in the marked point process, the coordinates are actually xi comma mi. So this will be defined as summation of fxi comma mi. So this can be any function from RD cross mark space. And I'm assuming the underlying PP has a intensity measure capital lambda. So for that, what I first do is I convert this exponential summation to product of exponential form. So this can be written as product of overall points, so exponential minus fxi and mi. Now, what we can do is we can break this. Yeah, and we notice that the points are actually coming from the original point process. So instead of writing this product over all xi mi belongs to phi tilde, I can just write it xi belongs to phi. It where phi is the corresponding point process, the underlying point process, which I know is a PPP. This will help us to solve it further because I know this function is Laplace function. So this function is PPP is Laplace function. So what I do now here is I take EXI product over all points. Now note that this phi tilde it has two randomness. One is phi and then another is the mi's given xi. So I break this expression in two parts. One is expectation is equal to phi, and then expectation with respect to mi goes inside the product because this does not depend on mi if I know all the points or if I know all phi. So now this is expectation with respect to mi given xi of this term condition on xi. So let's note that this function, when I compute the expectation with respect to mi, this will just be a function of gxi. So if I write instead of this as gxi, this will be expectation of e phi of product over gxi, which is a PGFL form. So it will be just exponential minus 1 minus gx lambda dx. This is noting that phi is a Poisson point process with this density, with this intensity measure. Okay. Now remaining is to compute this gx. So gx, if you look at, is the expectation of this function. So this is just integration of exponential minus fxm of new x dm. Okay, this is the probability distribution of m. Can you integrate it over the whole mark space? So if I write that back also, what I get is Laplace function is given as exponential minus 1 minus integration of exponential minus fx nu dx lambda dx. Okay, so there are multiple ways you can write this. One is this one. Second is I can just use the fact that integration over m of new dx is just 1, so I replace that, and then I can take this term common. So I get 1 minus exponential minus fxm, and then new xm and lambda dx. And we note that if the Campbell mattress measure is just dxtm is equal to this, so instead of that, I can write this. This is just lambda functional exponential minus integration of 1 minus exponential minus fxm into lambda Campbell mattress measure, which just tells the number of points, that points are in dx and the marks are in dx. Okay, so this is in the this is a Poisson process, PG Laplace functional with the intensity measure. This. Okay, this just proves that the mark point process is nothing but a PPP with this modified PPP with this intensity measure. It is also interesting to note a second form, that if I instead of writing this, if I just write it exponential, I'm given x of this one. And that is also used many times. That just to note that this term is nothing but the expectation of exponential minus fxm with respect to the mark distribution given x. This is the palm distribution of mark.